In this video, we're going to solve one practice question on fixed cost formulation. Question number 8 from chapter 12. So in this question, we have a company that is operating one plant at San Luis right now, but is considering additional one or multiple other plants in order to be able to satisfy the demand of its distribution centers. So the company is operating right now at San Luis with a capacity, annual capacity of 30,000 units. So all the numbers are actually annual. So I'm gonna not use annual word, but all the fixed costs, all the capacities are in a 1-year planning horizon. So just keep that in mind. As the company has the possibility of opening new plants at either of these 4 locations: Detroit, Toledo, Denver, and Kansas City. And for each one of these cities, for each one of the proposed plants, we know exactly the annual capacity. We also know the fixed cost. So if the company decides to open a plant, let's say at Detroit, it's going to cost the company a fixed amount of $175,000, and it's going to only provide a capacity of 10,000. Whereas if you open another plant, a new plant at Kansas City, it's going to cost you $500,000, a fixed cost, but then it's going to give you up to 40,000 of a new product that you can ship to your distribution centers. The company needs to provide the products to, ship from these plants to 3 distribution centers. 4 distribution centers, we have their annual demand, and their demand has to be their demands have to be satisfied. So we need to make sure. Right now we don't have enough capacity. The capacity at San Luis was 30,000 units, but what we need right now is 70,000, 30, 20, 20, 70,000 is the annual demand. We're short for 40,000 right now. So we need additional at least 40,000. One or multiple plants with at least 40,000, a collective capacity of 40,000. That's what we need. But then, so we had a fixed cost of opening a plant, and then we have a variable cost, which is the distribution cost or shipment cost per unit. So the nature of these costs is a variable cost, right? So out of, we have the shipping cost per unit for each plant, from each plant to each one of these distribution centers. So 5 plants, one of them is actual, the other 4 are potential. In any of them or in a combination of them, we can open facilities, we can open plants. But in this table, we have the transportation cost, the shipment cost per unit of product, all right, from each origin to each destination. 5 by 3, 15 possibilities in terms of shipment. So the question asks us to formulate a mixed integer programming model that could be used to help the company to first determine what plant or plants to open and how to actually satisfy the demand. Ultimately, we want to satisfy the demand, and we need to understand how we're going to satisfy the demand. How we're going to ship the items from each origin to each destination. So we want to come up with a distribution plan. So that's also a part of our decision. In part B, what is the optimal cost? What is the optimal set of plans to open? So what are the, actually, it asks us to solve, formulate, and solve. We're not gonna do part C in this video, but I'm gonna post another video that shows you how to look for either an alternative solution or a second best solution to when you have a integer programming. So we'll talk about this one last part in another video. Maybe I won't solve this one, but I'll show you the approach and you can use it to complete the solution of this problem. All right, so if I want to show you the network, so we have solved distribution problems, distribution optimization or transportation optimization problems before, and it's exactly the same with the addition of some binary decisions that we have to make, whether or not to open a plant at certain origins, at certain location. So some of our origins are not 100% certain, right? So we have a certain plant at San Luis. It's operating right now with a capacity of 30,000, but these are not operating yet. We have to make a decision about them, but the nature is the same. We have a distribution plan to make. So if we want to draw the network, it's going to look like this. So we have a list of plants, a list of origins, and a list of destinations, a list of distribution center, sellers, buyers, right? And then we have, for each one, we have the capacity, production capacity, demand, right? The constraint that we have here is that we want to satisfy these demands and we want to minimize the cost. So this will make sure that we will get a feasible solution for sure. But then out of this list of 5 plants, 4 of them, as you can see here, only San Luis is for sure, but the other 4, they have to be decided. They have to be determined based on, I mean, our model has to dictate that. Whether Detroit, Toledo, Denver, or Kansas City, which one of these, which one or which ones of these 4 we're gonna open. We're gonna have our proposed facility, proposed plan to be actually operating. 5 by 3, 15 routes that we have to decide about the number of units of items to be shipped using each one of these routes. So 15 decision variables plus 1, 2, 3, and 4 decision variables for establishing new plans in the new proposed location. All right. So these are basically my decision variables. How many items to be shipped from each route, from let's say origin I to destination J, plus I need to make 4 binary decisions. So if I go back in my sheet here, in this actually in the second sheet, I have the list of all the parameters here. But I'm gonna write down the formulation here and then we go to the second sheet and solve it there. So part A, formulate a mixed integer. It's gonna be a mixed integer because we have both continuous variable for the amount of shipment plus the binary variables for the plant to open or not, right? So I'm gonna write down the decision variables. So first of all, I'm gonna call it yi, and it's gonna be whether or not to open a plant at location I. And I can be either 1, 2, 3, or 4. So I'm assuming Detroit is 1, Toledo 2, 3, 4, and then San Luis is my 5th location. All right. So that's my decision variable. And these are binary. 0 or 1. 1 if 0 or 1. 1 means we open. We decide to open. 0 means no, we reject to open. And then we have 1xij, which is the amount or the number of products to be shipped from plant I to DC J, where I is where I is 1 to 5. All right, so I is my list of plants, and I'm including San Luis as well. 1, 2, 3, 4, and San Luis the 5th. And J can be equal to 1, 2, or 3. J equal to 1 for Boston, 2 Atlanta, 3 Houston. Okay. So that is, just merge it maybe. Yeah. All right. So this is my list of decision variables. 5 by 3, 15xij, and 4yij. So I have 19 in total. 19 variables in total. All right. Now, objective function. Objective function that I want to minimize in this case, everything, all these figures that we have in this question are cost. So I would like to minimize the total cost. And then cost is, we have a fixed cost plus a transportation cost, which is right here. So first, let me write down the cost of the fixed cost. So 175,000 times Y1. So I have to pay this cost if I open a facility at Detroit at location 1. So 175,000 times Y1. So if Y1 is 0, this is going to go away. I won't pay this cost. But if Y1 is 1, then my cost goes up by 175,000. So when I multiply this number by Y1, that is going to give me the actual cost of my decision. If the decision is 0, don't open a facility at Detroit, so nothing, no cost. If the decision is yes, I'm going to open a facility at Detroit, then I have to pay this cost. 175,000 is going to be my cost of that decision, plus 300,000 Y2 plus 75,000 Y3 plus 500,000 Y4 times Y4. All right. So that is my That is the fixed cost. Yes, the total annual fixed cost of opening facilities. Plus, so we're not done yet. So the cost function continues, and plus the distribution cost. And then the distribution cost depends on Xij, the amount of products shipped from each location, from each origin to each destination. So it's going to be 5 times X11 plus 2 times X12 plus 3 times X13 plus 4 times X21 plus 3 times X22 plus 4 times X2, 3, and so on, all the way to 3 times X5, 3. So I'm just gonna, as long as you understand, I'm gonna go with 5X11 all the way to 3, 5X11 plus, I just write it for the last one, 3 times X5, 3. All right, X53 is the amount shipped from the origin 5, which is San Luis, all the way to destination 3, which is Houston. All right. This one is identified as cost. Let me just add this. Yeah. So yeah. I did not write all of them down because it's gonna be a long function. So, but you got it, right? 5 times X11 plus 2 times X12 plus 3 times X13 all the way to 8 times X51, 4 times X52 plus 3 times X53. So that's the cost function. And now the constraints that we have to respect. First of all, we have a demand that has to be satisfied. So the amount that is shipped to each one of these cities, to each one of these distribution centers, has to be enough, has to be more than the annual demand. So items shipped to Boston should be greater than, so I would write it demand constraint, because we have at least two types of constraints. We have a demand constraints, and we also have a connecting constraints, because these two sets of decision variables should be logically connected. You can't ship from a plant unless you have a plant there, right? So Xij for I cannot be positive unless Yi is positive, unless you have a facility open there. So we'll talk about the connection in a minute, but let's just do the demand constraint right now. So the total number of units shipped to Boston is going to be X1. So I'll write Boston, Atlanta, and then Houston. The total number of items shipped to Boston is going to be X11 plus X21 plus X51. So the items to Boston can come from Detroit, location 1, 2, 3, all the way to 5, San Luis, right? That has to be greater than or equal to 30,000. X1, 2 plus X2, 2 plus X3, 2 plus X4, 2 plus X5, 2 has to be greater than or equal to 20,000. For Houston, X1, 3 plus X2, 3 plus x33 plus x43 plus x53 should be greater than or equal to 20,000. So that's the demand constraint. We also have a supply constraint, which we can write it right now, or we can actually use these capacities in our connecting type of constraints, because we have to connect these variables, and you know how these are connected. If you don't open a plant at Detroit, you won't be able to ship anything from Detroit, right? So you have to make sure that these variables are somehow connected. All right. So demand constraints, and then we have a connecting constraint. And the connecting constraints, you remember those. We had continuous variables less than or equal to the binary multiplied by a large number. And again, in this case, continuous is the amount that is shipped from each plant. All right. That has to be less than or equal to the binary variable regarding the plant multiplied by the large number. And the large number in this case is the annual capacity. So the items shipped from Detroit are going to be either 0 if we don't open a facility at Detroit, or going to be any number between 0 and 10,000. So I'm going to write it for each one of these 5. Let me just get this list from here and type it here. So for Detroit, the continuous variable, the amount of items shipped from Detroit is going to be x11 plus x12 plus x13. The items shipped from Detroit, right? That has to be less than or equal to y1, whether or not we're going to have a plant at Detroit, multiplied by the annual capacity at Detroit, 10,000. So now just take a look at this one and see what this does actually. So if you have a facility at Detroit, if you decide not to open a facility at Detroit, what happens is that Y1 is going to be 0. If Y1 is 0, 0 times 10,000, the right-hand side is going to be 0. So some of Xij's, X1j's are going to be forced to be 0, right? If they want to, the sum of them, sum of non-negative values, if they want to be negative, if they want to be 0, it means that all of them should be 0. All right. If this is 0, it'll force the other 3 to be 0, the other continuous variables connected to Detroit, right? If this is 1, it allows x11 plus x12 plus x13, sum of the 3, to take any positive value as long as it's smaller than or equal to 10,000. So that's what this constraint does. And I'm sure you guys can write it down for the other ones, but I'm going to write down for San Luis also, we need to write it down, even though we have a facility. So Y5, actually, if we had to decide about that, we should have put Y5, but now that it's in there, we just put the 30,000. So it's going to be 5, 1 plus 5, 2 plus 5, 3. The total amount of product, the total number of products shipped from the 5th San Luis, 5th city, should be less than or equal to its capacity, which is 30,000. So for San Luis, it's 30,000 fixed. But for Detroit and for other cities, it depends. The capacity depends on whether you open it or not. So you multiply it by the corresponding binary variable, and then that's going to give you the right hand side. So this is the formulation, but remember, you have to keep doing it for the other three. Let me just do it. X21 plus X22 plus X23 should be less than or equal to Y2 times 20,000. X31 plus X32 plus X33 should be less than or equal to Y3 times 30,000. X41 plus X42 plus X43 should be less than or equal to 40,000, or Y4 times 40,000. So that is the formulation. And we took care of the capacity, we took care of the demand, we have the objective function, everything is set up. So I'm gonna go ahead, go to the other tab. So this is the formulation, this is the answer to part A of these questions. This is the formulation. For part B, for solving the model now, I'm gonna go ahead and use the parameters that I have. So first, objective functions, first decision variables. I need to make 19 decisions. So first, the amount of items to be shipped, number of items or amount of items to be shipped from each plant to each distribution center. So that's the decision that we are making. All right. And these are to be determined by the model. So 15 continuous decision variables plus 4 binary decision variables, whether to open or not. Okay. So we need to make these 4 decisions as well. Actually, I'm gonna change the color to something else. Yes, because the types of these two are different, right? These 4 are going to be binary. These 15 are going to be continuous. So decision variables, and then objective function. Objective is the cost, which we want to minimize. And I'm just going to write down the function over here. It's going to be the sum product of the, actually, let me write down the fixed cost first. The annual fixed cost by the decision regarding opening facilities, opening plants, plus the sum product again of variable cost of distribution, and which is 5 by 3, 15 by these 15 decisions to be made. All right, so that is going to give us the objective function, which is the cost. And I'm going to write down the formula right here. Okay, so that's the objective function that we want to find. All right, next, the set of the constraints. We have a demand to satisfy, and we also need to write down the connecting constraints and the capacity constraint for San Luis. So for the demand first, for either of the threes, we have demand constraint. For each one of these cities, the total amount shipped to, let's say for Boston, let's just do it for Boston and then we can copy the formula. The sum of items shipped to Boston has to be greater than or equal to the total amount needed for Boston. All right. So now I can just drag my formula to the right. Let's say for Houston, the total amount shipped to Houston should be greater than or equal to 20,000. 20,000, 30,000. All right. Just to show you the formula here. And okay, so that's the demand. That's the demand constraints. Now we have a connection, a connecting type of constraints. The total amount shipped from Detroit, sum of the three, should be less than or equal to the total capacity of Detroit multiplied by this binary variable. The total capacity of Detroit multiplied by this binary decision. So I'm gonna write down maybe over here. Okay, let me just copy. And then we have over here, we have connecting constraints. So for Detroit, sum of items shipped from Detroit sum of items shipped from Detroit has to be less than or equal to the maximum capacity of Detroit multiplied by maximum capacity and 2 multiplied by the binary decision regarding that. All right. So that is how we write down the connecting type of constraint. And we can just copy and paste these for the other cities, except for San Luis. We don't need to multiply it by, I mean, I can put 1 here, but I don't need to. I can just simply remove this and have 30,000. So for San Luis, the sum of items shipped from San Luis to either of these cities should be less than or equal to 30,000. For the other ones, let's say for Kansas City, it should be the decision whether or not you open multiplied by the actual annual capacity of that plant. So our formulation, our actually spreadsheet model is pretty much ready. I think we can now go ahead and put it on solver. So on our solver, we want to minimize the cost. We wanted to minimize the cost, and the cost is right here by changing 19 decision variables. So these are my continuous ones, comma, and these 4. So set of 19 decision variables subject to the demand constraints, left-hand sides greater than or equal to the right-hand side. So demand constraints plus the connecting constraints. I have the left-hand side less than or equal to the right-hand sides. And also, I have to make sure that my four variables here are defined to be binary. Okay. And then make sure to change the simple solving method to simplex LP. So we're minimizing the transportation cost. We're minimizing the total cost, which contains transportation cost as well as the fixed cost. All right, M18, yes. And then by changing these 19 decision variables subject to the demand constraints as well as the connecting constraints, right? And then the binary decision variables. All right, and then solve. So great, Excel found a solution. Let's check it out. $860,000 is going to be the minimum cost for us to be able to satisfy the demand. First of all, let me just replace these weird numbers with 0, these small, you see E minus 12, it's actually 1 divided by 10 to the power of 12. It's a very tiny number, so 0, 0, 0. All right, so this is now our answer. We are opening only one facility at Kansas City, and it's going to add the capacity by 40,000. We knew that the capacity for Kansas City was 40,000, and we needed only 40,000 because our demand was 70,000 and our firm supply at the moment that was provided by San Luis was 30,000. So we were short for 40,000. So by opening just one plant at Kansas City, we're bringing up the capacity to 70,000, 30,000 by San Luis, 40,000 by Kansas City. And this is how we satisfy the demand. Boston only from San Luis, Atlanta, and Houston only by Kansas City. And this is the minimum cost. And as you can see, all the demand constraints are satisfied. And also, all the connecting constraints are satisfied. Kansas City and San Luis were using up all their supply capacity.